Hello and welcome back to Introductory Astronomy. Today we're going to talk about black holes. Remember how neutron stars are the result of a type II supernova explosion, and they are composed almost entirely of tightly packed neutrons. However, if the neutron star exceeds about 3 solar masses, then gravity wins the battle with pressure once and for all, and the star's central core collapses forever. Stellar evolution theory indicates that this is the fate of any star whose main sequence mass exceeds about 25 times the mass of the Sun. When that happens, we end up having such an intense gravitational force that even light cannot escape, and the remnant has become a black hole. The radius at which the escape speed from the black hole equals the speed of light is called the Schwarzschild radius. And remember, the speed of light is 300,000 kilometers per second. You can calculate the Schwarzschild radius for any object using this simple mathematical formula, where r sub s corresponds to the Schwarzschild radius, and remember g is the gravitational constant, m is the mass of the object, and c, of course, is the speed of light. So take a minute and calculate that for the Earth and our Sun. Figure out the Schwarzschild radius if they were to collapse into a black hole. If you do that, you'll find that the Earth's Schwarzschild radius is about 1 centimeter, and the one for the Sun is about 3 kilometers. Now, once the object has collapsed into a black hole, the Schwarzschild radius takes on another meaning. It is what we call the event horizon. Nothing within the event horizon can escape the black hole, not even light, which is why we call them black holes, because light does not escape them and we cannot see them. Now, in that picture right there, you see singularity right in the center. A singularity is a name for a point where the density of matter and the gravitational field approach infinity. So that corresponds to the center of a black hole. Let's talk a little bit about Einstein's theories of relativity. Now, Einstein's theories of relativity are very complicated, and in terms of the scope of this course, we're just going to talk in very general terms about the most highlighted and general basic concepts that you should know. For example, within special relativity, it's very important to understand that the speed of light is what we call the speed limit of the universe. It is the maximum possible speed. And what's very interesting about that, and Einstein was the first to figure it out, is that it is always measured to have the same value for all observers. So what do I mean by that? Let's take a look at frame A. If you're in your car driving at 100 kilometers per hour and you fire a bullet at 1,000 kilometers per hour relative to the car, the observer will see the bullet from the ground, will see the bullet traveling at 1,100 kilometers per hour. So the outside observer sees a speed equal to the sum of the speeds of the car and of the bullet. Let's take a look at another example now with light. What if you are in a spaceship that travels at a speed 1/10 of the speed of light, and you turn on your light beam? That, of course, is going to travel at the speed of light. Well, an outside observer will still see the light beam to be traveling at the speed of light, regardless of the speed of the spacecraft. So this tells you that the speed of light is independent of the speed of any source or any observer. Couple of other things that Einstein talked about is that there is no absolute frame of reference and no absolute state of rest. And space and time are not independent, but are unified as space-time, what we call our four dimensions, the three spatial dimensions and the fourth time dimension, space-time. In terms of general relativity, it is important to understand that it is impossible to tell from within a closed system whether someone is in a gravitational field or accelerating. And I'm going to try to explain that using the Einstein's famous elevator example. If you have someone in a closed elevator floating in space, and he feels a force exerted on his feet by the elevator floor. Well, Einstein reasoned that no experiment conducted entirely within the elevator can tell this person whether the force is A, due to the gravity of a nearby massive object, or B, caused by the acceleration of the elevator itself. Matter in general tends to warp space-time, and in doing so, it redefines straight lines, meaning the path a light beam would take. If you take a look at the picture right here and you envision a pool table made of a thin rubber sheet, you know that if you put a weight on it, it will start sagging. Likewise, space is bent or warped in the vicinity of any massive object. What we call a black hole occurs when this indentation, caused by the mass of the hole, becomes infinitely deep. So as the weight increases, so does the warping of space. In frame B here, you see a ball rolling across the table is deflected by the curvature of the surface in much the same way as a planet's curved orbit is determined by the curvature of space-time produced by the sun. In the late 19th century, Michelson and Morley did an experiment to measure the variation in the speed of light with respect to the direction of the Earth's motion around the sun. They found no variation. Light always traveled at the same speed. This is what later became the foundation of special relativity. Taking the speed of light to be constant leads to some counterintuitive effects, such as length contraction, time dilation, the relativity of simultaneity, and the mass equivalent of energy. And your book goes into more detail. How about space travel near black holes? The gravitational effects of a black hole are unnoticeable outside of a few Schwarzschild radii. It is a common misconception that black holes suck in material. They don't do that any more than an extended mass does. Now, matter encountering a black hole will experience enormous tidal forces that will both heat it enough to radiate and tear it apart in what we commonly call as spaghettification. So you will be stretched and heated infinitely thin. A probe nearing the event horizon of a black hole will be seen by observers as experiencing a dramatic redshift as it gets closer, so that time appears to be going more and more slowly as it approaches the event horizon. This is called a gravitational redshift. It is not due to motion, but due to the large gravitational fields present. The probe itself, however, does not experience any such shifts. Time would appear normal to anyone inside. If you were to leap into a black hole of a few solar masses from a distance of 1 AU, the gravitational pull would not be very large in the beginning, but as you got closer to the black hole, you would travel faster. Your watch would tell you that you fell for about 2 months before you reached the event horizon. Your friends, however, who stayed behind would see something very different. They would see you falling slower and slower as you came closer to the event horizon due to time dilation. Time slows down in curved space-time. They would never actually see you cross the event horizon. For them, you would fall more and more slowly until you seemed hardly to move. Here we have an illustration of a photon escaping from the vicinity of a black hole and how it uses up a lot of energy in doing so. Since it cannot slow down, because it travels at the speed of light, what will happen to its wavelength? Well, its wavelength gets longer and longer due to the gravitational redshift. So let's take a closer look at this picture. As a photon escapes from the strong gravitational field close to a black hole, it must expend energy to overcome the hole's gravity. This energy does not come from a change in the speed at which the photon travels, since we know that its speed is always constant. Rather, the photon gives up energy by increasing its wavelength. Thus, the photon's frequency changes, and the photon is redshifted into a less energetic region of the spectrum. This picture shows the effect on two beams of radiation, one of visible light and one of X-rays, emitted from a space probe as it nears the event horizon of a 1 solar mass black hole. Note that the light is not coming from within the black hole itself, but only its vicinity. The beams are shifted to longer and longer wavelengths as they move further from the event horizon. So, what's inside a black hole? No one knows, of course. Present theory predicts that the mass collapses until its radius is 0 and its density is infinite, but it is unlikely that this is what actually happens. Until we learn more about what happens in such extreme conditions, the interiors of black holes will remain a mystery. So how do we know that they actually exist and they're not just a mathematical construct? Well, black holes, of course, cannot be observed directly, as their gravitational fields will cause light to bend around them. If you take a look at this picture right here, you see how a massive black hole makes it impossible to observe the hole as a black dot superimposed against the bright background of its stellar companion. Let's take a look at Cygnus X1. This bright star has an unseen companion that is a strong X-ray emitter called Cygnus X1, which is thought to be a black hole. So why do we think that? If you look at frame A, the brightest star in this photograph is a member of a binary system whose unseen companion, which we call Cygnus X1, is believed to be a black hole. If you take a look at frame B, that's an X-ray image of field of view outlined by the rectangle in part A. Of course, X-rays cannot be seen directly, and X-rays emitted by the Cygnus X1 source were captured in space by an X-ray detector aboard a satellite, changed into radio signals for transmission to the ground, and changed again into electronic signals that were then viewed on a video screen from which this picture was taken. The existence of black hole binary partners for ordinary stars can be inferred by the effect the holes have on the star's orbit, or by radiation from infalling matter. So here's the artist's conception of a binary system containing a large, bright, visible star and an invisible X-ray emitting black hole. This painting is based on data obtained from detailed observations of Cygnus X1. So putting all this together makes Cygnus X1 a very strong black hole candidate. Its visible partner is about 25 solar masses. The system's total mass is about 35 solar masses, so the X-ray source must be about 10 solar masses. Hot gas appears to be flowing from the visible star to an unseen companion. Short timescale variations indicate that the source must be very small. So all these things put together indicate that Cygnus X1 is most likely a black hole. Now, there are several other black hole candidates as well, with characteristics similar to Cygnus X1. In fact, the centers of many galaxies contain what we call supermassive black holes that have masses of million solar masses. This is a galaxy 3C296. The blue color shows the distribution of stars in the central elliptical galaxy, and the red shows huge jets of radio emission extending 500,000 light-years across. Recently, evidence for intermediate mass black holes has been found. These are about 100 to 1,000 solar masses. Their origin is not well understood yet. Right here you see X-ray observations in the inset of the interior of the starburst galaxy M82, shown at the top picture. It's about 100,000 light-years across and 12 million light-years away. As you can see, there's a collection of bright sources thought to be the result of matter accreting onto intermediate mass black holes. The black holes are probably young, have masses between 100 and 1,000 times the mass of the Sun, and lie relatively far, about 600 light-years, from the center of M82. The brightest and possibly most massive intermediate mass black hole candidate is marked by an arrow. Here's a table of some candidates for black holes. As you can see, they all have more than 3 solar masses. Cygnus X1 is the first one on the table, and its companion star is a B0 supergiant, and it has an orbital period of 5.6 days. Now, how do we know that we're seeing a black hole X-ray nova versus a neutron star X-ray nova? Here's how you can tell them apart. Black holes. Accreted matter disappears beyond the event horizon without a trace. Anything that passes the event horizon, mass or light, is gone. If we have a neutron star scenario, then the accreted matter produces an X-ray flush as it impacts on the neutron star surface. Your book talks about a couple of tests of general relativity. This one took place during the solar eclipse of 1919. The deflection of starlight by the sun's gravity was measured then, and the results agreed with the predictions of general relativity. As you can see, the apparent position of the star versus the actual position of the star. Another prediction was that the orbit of Mercury should precess due to general relativistic effects near the sun because of the huge mass of the sun. And the measurements that they made agreed with general relativity predictions. General relativity predicts that orbiting objects should lose energy by emitting gravitational radiation. The amount of this energy is tiny, and these waves have not yet been observed directly. However, a neutron star binary system has been observed. The orbits of the stars are slowing at just the rate predicted if gravity waves were carrying off the lost energy. So we built LIGO, the Laser Interferometric Gravity Wave Observatory designed to detect gravitational waves. It has been operating since 2003, but no waves have been detected yet. Here's a little summary of Chapter 22. A supernova explosion may leave behind a neutron star. Neutron stars are incredibly dense, spin very fast, and have great magnetic fields. Neutron stars may appear as pulsars due to the lighthouse effect. A neutron star in a closed binary may become an X-ray burster or a millisecond pulsar. Gamma-ray bursts are probably due to two neutron stars colliding or a hypernova. If a supernova core remnant is more than about 3 solar masses, then it collapses into a black hole. We need Einstein's general relativity to describe black holes, because relativity describes gravity as the warping of space and time. Anything entering within the event horizon of a black hole cannot escape. The distance from the event horizon to the singularity is called the Schwarzschild radius. A distant observer would see an object entering a black hole subject to extreme gravitational redshift and time dilation. Material approaching a black hole will emit strong X-rays. A few such X-ray sources have been found and are black hole candidates. Study Chapter 22.5 through 22.8. Be able to describe how black holes are formed and discuss their effects on matter and radiation in their vicinity. Be able to describe Einstein's derivatives of relativity in the most general terms, and be able to discuss how they relate to neutron stars and black holes. And also be able to explain how black holes may be detected. Until next time.